What you are looking at is footage stabilized using Gyroflow, an open source tool I've been working on over the past few months, which uses the gyroscope information logged by multi-copter flight controllers for stabilizing the onboard HD footage. The advantage of gyro-assisted video stabilization is that there's no guesswork involved, so if you have any foreground objects moving around or changing light conditions, the stabilizer does not get confused. This is especially useful for fast forward-moving motion seen in FPV-type footage. Since the first paper was published about the subject back in 2011, a number of both commercial and non-commercial solutions have appeared. For GoPro cameras, there's Real Steady Go, which uses the internally locked gyro information for video stabilization. For larger cinema-style cameras or DSLR cameras, there is SteadXP, and some manufacturers even have their own solutions, such as Insta360 with their flow state stabilization and Sony with their stabilization solution in the Catalyst Browse. It should also be mentioned that there's another open source project called Virtual Gimbal, which is in many ways much more advanced than Gyroflow in terms of all the image processing stuff. From what I've seen, they've achieved excellent results with rolling shutter correction for DSLR type cameras. When I was getting started in FPV, I wanted to try out a little bit of, cinematic style footage, and many of these options were a bit out of my budget. So of course the natural reaction was, okay, so I know literally nothing about image stabilization or image processing, but there are these papers floating around, so why not make something completely from scratch? It's going to be like following a cake recipe. It's going to be fun and exciting and yeah. In the beginning, the results looked something like this. Then a few months later, it looked something like this. And then now it looks something like this. It should also be mentioned that a bit parallel to the development of Gyroflow, another tool appeared called Blackbox2GPMF. It was developed by Magicae and later maintained by Attila Fustos, and is a way of emulating GoPro metadata for use with Real Steady Go. It works especially well for action cameras with similar lens distortions to existing GoPro cameras. Now back to Gyroflow. More recently, a number of people have expressed interest in using the software, and some people have gotten good results, some people have gotten not so good results, and the whole workflow has been a bit of a mess. So over the past week or so, I've been improving the workflow a bit, improving the user experience and user interface, as well as fixing bugs and all the usual stuff. The tool is now at a point where it is somewhat usable. So in this video, I'm going to guide you through pretty much everything there is to know about using Gyroflow. This video will be split into a number of different chapters, and you should be able to select the chapters down below if you want to skip ahead. I'm going to cover both the gyro logging process using Betaflight or similar flight control firmwares. I'm also going to briefly cover the physical setup. I'm also going to go over the installation process of the software, as well as how to use the software, both the image calibration and the image stabilization. All right, let's begin. Now let's go over the process of logging gyro data using a flight controller running Betaflight. The same process should be applicable for similar flight firmwares. And just as a full disclaimer, I haven't actually tried many of these things myself since I haven't done a bunch of flying recently. So this is mostly based on posts by others in the Facebook group. So if you have any questions about any of this, please check out the Facebook group where there are a bunch of resources about the topic. So now let's connect to in this case, a quadcopter using the configurator. You can see it moving around and all the usual stuff. Over on the left-hand side, we can go over to the black box tab, which is the one we're interested in looking at. We can see here that this flight controller in particular, it's a Mamba F4405. This one has 16 megabytes of flash space available on the flash chip. This is usually enough for something like 2 or 3 different flights. But in the next version of Betaflight, in Betaflight 4.3, then I think they said something about an option to limit the information stored onto the black box. So in that case, it should be possible to achieve more flights on the limited amount of space available. Now let's go over to the options available over here. In this case, on the first one, you select whichever device you're logging to. In this case, it's the onboard flash. But if you're using something like the Open Lager, you can also log to a serial port as well. I can imagine it's if you have an SD card mount on the flight controller, it's probably some option over here, I'm guessing. Now, on the next one, we are able to select the logging rate. And for this, we only will need something like 1,000 or 500. Anything above is a bit overkill. And for a comparison, the GoPro Hero 8 logs gyro data at around 200 Hertz. So if the data is clean, if there's not too much noise going on, a 500 or 1,000 should be more than enough. And for the debug mode, just leave it to none. We don't really need any of this information. Now, you may be wondering, are there any ways of expanding the space available? And the answer is yes, you can use the Open Lager device as previously mentioned. But another nice way, which was shared over in the Facebook group, is to desolder the flash chip on your flight controller. And since the communication between the flight controller and the flash chip is using SPI, you can wire up a micro SD card using the same interface. So the important thing about the physical setup is that the gyroscope is able to measure the movements of the camera. So if the camera is ultra soft mounted and if it sways around while it's flying, it's not going to work out since the main gyroscope in the flight controller doesn't actually measure the movements of the camera. What you might do is to use less soft mounts maybe. Usually from what I've seen, a TPU mount works fairly well. It's pretty much rigid when it comes to major movements, but it still isolates many of the high frequency vibrations which are not really stabilized that way. So TPU mounts seem to work fine, but if you have something crazy with rubber bands or whatnot, it's probably going to cause problems. What you might do instead is to, instead of using the main flight controller for logging, you can use a secondary flight controller. You can take a little random flight controller and mount it closer or directly onto the camera itself and use that to log the gyro information. The advantage here is that, of course, the movements match 100%, but I guess you also lose out on some of the fancy filtering which is found on the main flight controller. But I mean, if it's soft mounted, it's probably going to be fine, I'm guessing. Now you may be wondering, if I'm using a secondary flight controller, how do I actually start and stop the logging? And the way you do that is to go over to the CLI tab. By default, the black box is going to log to the black box whenever the quadcopter is armed. And that usually works fairly well if you're using the main flight controller. But if you're using a secondary flight controller, what you might do is to write set black box mode. Let's see. So we have a number of different options. In the normal mode, it's going to log to the black box whenever it's armed, but you can set it to always, and in that case, it's going to log whenever the flight controller is powered on. But as I said, I haven't actually tried any of this myself, so please check out the Facebook group where there's a bunch of information. Now, when you go ahead and capture the footage, what you want to make sure of is that you know the camera angle. That's only applicable if you're using the main flight controller, but just something to keep in mind. It's of course pretty easy if you have a fixed camera mount. Another thing, which is not exactly super critical, but it's going to make your life a lot easier down the line, is that you want to start the gyro recording and the video recording somewhat close to each other. And by somewhat close, I mean like 10 or 20 seconds is probably going to be fine. But you don't want to start your video recording and wait 10 minutes before starting the gyro recording. It can work, but it's just going to be a bit annoying to set up. So yeah. Now I'm going to cover the installation process for Gyroflow. First of all, you want to go over to the main website. I know, very fancy, there's a website called gyroflow.x-alpha. Very creative, right? Because XYZ, gyros and all that. It's going to redirect to this different page, but just ignore that. If you want to download the Windows executable, you click on the Downloads button. By the time this video is out, you should be able to see a Windows executable available here, and maybe also executables for Mac and Ubuntu, but we'll see about that. Alternatively, you can also go over to the GitHub repository, which is linked right here, and click on the releases button over on the right-hand side. This should give you another way of downloading the executables if you prefer, but it's basically the same thing. The links from the main website is basically linking over to the GitHub. And you also click on the Lens presets download button right here. This is going to give you a number of presets which have been used for testing purposes. So I have the files locally on my computer. So I'm going to drag them over to my desktop, since I'm fundamentally a very messy person. Now you should see that you have a Windows executable in my case, and a zip file containing the presets. And once again, I have the file already extracted. So to check if your installation has been successful, you basically just double-click on the Windows executable. After a few moments, the main window should appear. There's this black box, which is the command window. It's going to show you messages or error messages or info messages. Basically, just have the command window open somewhere, just so you can monitor the process. And here we go. We have the main launcher. We can check for updates and see if everything is fine. Something which may be a problem for a Mac or perhaps Ubuntu or other Linux variants is that you need to install FFmpeg separately. And that's going to give you a bunch of errors if there's a problem with your FFmpeg installation. What you then do is you go to ffmpeg.org, and you should be able to navigate around and download whatever version corresponds to your operating system. And that's pretty much it for the installation process. Now I'm going to cover the camera calibration process using Gyroflow. First of all, in the main launcher, you click on the Camera Calibrator button, and you should be met by a dialog box asking for the chessboard size. By default, it's set to 9:6, but if you want a larger chessboard with more features to be detected in each frame, you can specify a different size. So, but let's just use something like 11:8. Click OK, and you should be met by a new window. This is the main calibrator utility. We have a few options for adding calibration frames, and we have a file button on the upper left menu. If you haven't captured a calibration clip, you need to click on File followed by Calibration Target, which is going to make a chessboard pattern appear. This chessboard pattern has the size which was previously specified using the dialog box. And you may be wondering, wait a minute, why in the world does this chessboard have 12 squares on the horizontal axis and 9 squares on the vertical axis, instead of the 11:8 as specified up above? But the reason is that we are counting the number of intersections between the square pieces, not the square pieces themselves. So what you need to do now is to take whatever camera system you want to be calibrating, and you need to use the settings which you want to calibrate for. The most important part is whatever settings change the field of view. So let's say you have a 1080p setting and a 4K setting, but if the field of view between the two stay the same, you only need to do calibration for one of them and just use the same one for the other setting. But if things like the aspect ratio or the field of view changes, you need to use separate calibrations for those. Of course, if you need to calibrate different lenses, you need to swap those out. You also want to basically disable anything which may influence the field of view of the final result. So if you have in-body digital image stabilization, you need to disable that as well, since it normally crops in a little bit. So what you then need to do is to capture your monitor. It should also be noted that your monitor needs to be flat, because otherwise everything is going to get confused. And what you need to do is to record your screen and move your camera around a bit to try to get a bunch of different angles. And I'm going to show you a calibration clip right now. Alright, time to do the camera calibration. I know this is absolutely riveting content, but it has to be done. This is using the wide-angle lens on my cell phone. So first of all, let's get a few nice close-up shots of the chessboard. View over to the edges, like so. And we also need to get a few angles from down below. Let's do something like this. And up above. You want to make sure that for each angle you want to add to the calibration, that you hold the camera as still as possible. This will ensure that there's not too much rolling shutter, which will affect the calibration. Now let's also do the corners of the chessboard. We'll do this by aligning the corners of the chessboard to the corners of the frame itself. And this will ensure that we get as much information about the camera distortion as possible all the way out to the edges of the image. Like so. And that should be fine for the calibration. Let's also, just for fun, get a few more angles. The more angles you get, the better the calibration is going to be. But usually something like this is probably going to be fine. Nice close up again. Oh geez. You have now seen how to capture the calibration clip. Let's now move on to the actual calibration process. So let's close the calibration chessboard. And we can now click on File followed by Open File to find our calibration clip. I'm going to use this one, which you hopefully just saw. Over on the left-hand side, I'm going to be placing the command window or the terminal, just to make sure that any errors will be monitored. So we can now go through the video. You can use the play button. If you click on this one, it should play. Or you can use this slider. It's really quite buggy, but I mean, it works, I suppose. So we now need to go through and find the frames which we want to add to calibration. So you ideally want to use frames where the whole chessboard is clear and sharp, and you don't want any sort of rolling shutter distortion or too much motion blur. So now let's add this one, for instance. Each time you click on the Add Current Frame button, it's going to detect the chessboard pattern, but it's not going to run the actual distortion calculation right away. So you can add a whole bunch of frames followed by process loaded frames, which is going to then calculate all the distortion stuff. So one thing which we can do is we can start off by adding a couple of frames. So the number of good frames in quote marks is now 2, and the number of processed frames is still 0. We can now click on process loaded frames, which is going to be calculating all the camera lens information stuff. And now you see something which you do not want to see. We see that the RMS error has jumped up to 300, and ideally the value of the RMS error needs to be below 1. So if whenever you see a large value for the RMS error, it means that something has gone wrong with the calibration. And I've noticed that in some cases, when you place the chessboard too close to the edge of the frame, you get this error, and it's something that has to be looked into. But for now, what you can do is to click on the Remove Last Frame button. Let's see if that helps. Nope. In that case, this thing is actually just to open the file once again. I know it's not optimal, but the good thing is that you only really need to do this once. So yeah. Okay, let's see. Let's add this frame, for instance. Okay, there we go. So for some reason, this frame works better than the last one. I have no idea why, but it probably has something to do with the camera model. But for now, you basically just mess around until it works. Okay, so now we see that the RMS error has a very low value. The RMS error is the root mean squared reprojection error. In other words, it's essentially the average distance between where the chessboard edges are expected to be and where they are actually found in the image itself. A low value for the RMS error does not mean that the calibration is good, but on the other hand, a very high value for the RMS error means that the calibration is bad, as you previously saw. So in this case, a low value, even though we only have one image, means that it only knows something about the image distortion around the center of the image, but it still knows nothing about the edges of the image. So what you can do after adding 1 or 2 images is to click on this button over on the right-hand side, the toggle lens correction button, which is going to give you a view of what the undistorted image looks like. And you can see now that the center of the image all looks great. All the lines are straight as they need to be, but around the edges of the image, it's still missing some information about the image distortion. So let's switch back to this one, and we can go through the video and basically just add a whole bunch of frames. And whenever you see, okay, like this, so in this case, the chessboard is probably too close to the edge of the image. So whenever you see that the RMS error is incredibly high, or alternatively, if you see that the undistorted result looks something like this, which is obviously, something has obviously gone wrong, what you then can do is to click on the remove last frame button to remove the last frame, and then process once again. So basically try to go through the video and add a whole bunch of frames. Okay, you see this one works fine. The RMS error hasn't gone above like 2, so it's fine. So basically just go through and add a whole bunch of frames. So that's what I'm going to do now. We need a few frames from down below, from up in front, from above, from the left and right hand side. And yeah, basically the more angles we get, the better the calibration is going to be. Oh geez. Okay, so over on the left hand side, we see that there's now an error. So something has gone horribly wrong. So what we might be able to do is to remove maybe the last 2 frames and see if that helps. Maybe. And maybe try to add a difference. Okay, that helped. So I mean the camera calibration stuff is really quite buggy. So basically just try to mess around. If it doesn't work, your best bet is probably to start over, but yeah. So we're going to add up here at all the different angles, right? You can also click on the play button and click on add current frame while you're watching the video. And in this case, it worked quite well. We can click on, we can see the undistorted result, and it actually looks kind of all right. So let's suppose that a bunch of frames have been added. Usually you want to go get something above 10. The more frames, the better, but there's really no need to get too many frames. The most important thing is that you need to get frames from all the different angles around the camera or around the chessboard. So yeah, you can see how buggy everything is. Okay, let's add this one. Oh no, so we can see this one, we placed the chessboard too close to the edge of the image, and the RMS error has jumped up. And now it looks something like this. So let's once again remove the last frame. And let's try to go through and maybe add a couple of other ones. Okay, this one worked fine. And we also have a few wonky ones in the end. This one is fine as well. And let's try this one. Yeah, that's fine. And let's also do this one. Okay, so let's say that you have added all the frames you want and you are happy with the results. Go over to the toggle lens correction and just make sure that all the straight lines in the video actually correspond to straight lines in real life and vice versa. And I mean, yeah, you can do more if you want, but this is fine for now. After you have done all of this, you now need to save the calibration file. And to do so, you go over to the right-hand side. So in this case, let's just, I mean, I use the cell phone camera, but that's not the most exciting thing in the world. So let's imagine that it's a DSLR camera with some lens instead. So let's say we have a Nikon camera. And the make is a D5100, which is what I happen to have right beside me at the moment. Let's now use a lens. Let's just say it's a Nikkor from 18 to 55. It's like the kit lens, you know. Just write something which describes whatever system you're using. The recording setting is going to be the important, especially if the different recording settings actually change the field of view. For instance, with GoPro cameras, shooting in wide or normal field of view actually changes how much cropping is done within the camera itself. So in this case, let's just say it's 1080p, 16 by 9, normal or something. And over here you can write whatever note you want. Yeah, if something happened during the calibration or just something else which may be important to whoever is going to be using the calibration, you can write it over here. So in this case, I'm going to just write something like, this is a test calibration, don't use it, exclamation mark. And over here you can write write your name or your handle or whatever. Now click on the export preset file and you should see that that a file name has been automatically generated to contain most of the important information. Now let's go over to, I have a folder called, let's see, I have a camera presets folder, but you can save it wherever you want. So in this case, let's save it over here, and let's click save. And you should now see that the lens distortion or the camera preset has been saved. One thing which you can do if you want to check if one of the existing camera presets actually work all right, you can essentially go through and open the file which you want to check. So let's open this one once again. You can then click on File followed by Open Calibration Presets and navigate over to, let's see if I can find it, navigate over to one of the existing presets. And let's just take this one. And you should be able to toggle lens correction, and you should see that once again all the straight lines map to straight lines. We can also try something else. So let's use this one, which is actually captured by the DSLR. And let's click on toggle lens correction. And you should now see that something doesn't really match up. You can also use this slider to zoom in a bit. You can see in this case, the result has not been undistorted as you would expect, right? So the straight lines are not straight. So this is just one way to check if your lens preset actually matches your camera. And that's pretty much it for the calibration stuff. I know it's really quite buggy, but yeah, you only need to do it once. So as you saw, the calibration process, at least at the moment, can be a bit annoying. So if you want to help out, you can go over to the website after making a calibration preset. Click on Add Lens Profile, and you can use this form to send in the calibration preset. If you have a new camera which has not yet been calibrated, you can do that, and you can help out. It is now time for what is arguably the most exciting parts of the process, the actual stabilization itself. To do so, you want to first of all load the black box files over to your computer. You can use the mass storage mode in the configurator application. You will have some BBL files or BFL files depending on something. I'm not completely sure what. After moving the black box files over to your computer, you want to make sure that all the files are nicely organized. That is, of course, not quite the case for me here, but you basically want to make sure that you know which black box file match with the video files. In some cases, you can even have multiple black box logs in a single file. And in that case, you want to open up the BBL file or BFL file using the Black Box Explorer. And in there, you are able to take a look at the different logs and make sure that they match. In this case, we only have a single log, but what you want to do, preferably, is to save the files as a CSV file. Gyroflow is able to load both the black box files or the CSV files. But usually if you save it as a CSV file, the processing is going to be a little bit quicker. And it's also useful to just take a look at the logs and see if there's excessive amounts of noise and to make sure that the logs match up with the video. You don't really need to do any sort of syncing over here if you started the black box log and the video somewhat close to each other. But to export the file as to export the log as a CSV file, just click on this Export CSV button, and you should be able to save it as a CSV file. It's going to automatically name your CSV file the same as the original black box file with a suffix of .bbl.csv. This is fine, and you just want to click Save. So in the same folder as your video file, Let me reload this real quick. So in the same folder as your CSV file, you should see that you have a BBL file, the original raw black box file, your newly created CSV file exported from the black box Explorer, as well as the original video file. And what this is going to do is, if you open the video file, which I'm going to show in just a moment, it's going to automatically detect whichever log file has the similar name to it. And it's going to preferentially pick the one with .bbl.csv. And if it cannot find this one, it's going to pick the .bbl file. I found in some rare cases it has trouble opening the BBL file, so if for some reason it doesn't work with your system, you can just export it as a CSV file. And that is of course required if you have multiple flights saved on a single black box file. Let's now go back to Gyroflow to do the stabilization itself. Once again, we want the command prompt or terminal over somewhere so we can monitor all the messages. And let's now click on the Video Stabilizer button to open the main stabilization user interface. We have a number of tabs and a whole bunch of different options, and this may look a little scary, but a lot of them you don't really need to touch, and I'm going to guide you through most of the important options. Let's now click on the Open File button to specify what we want to use as the input file. I have a test clips folder, and I'm going to find nice crash underscore hero7.mp4. If you have something like like a QuickTime file or an AVI file, you can also select the file type over here. But let's open this one. And you should see that the black box file has automatically been filled in. If you want to remove this one, we can just click on this and open the file once again. And in this case, it was the one called nicecrash underscore hero7.bbl.csv. But we can also select the raw.bbl file. But in this case, let's just select the CSV file. It should have automatically detected the file type based on the file suffix. But if you use a .bbl file or black box file, you should select a raw black box log over here. And for a black box CSV, just select the second option. You can also remove the black box file over here. And this is going to try to treat the file as a GoPro file. In other words, it's going to extract the gyro information directly from the file itself. So in this case, we want to use the black box file, and I'm going to use the black box CSV file. What you then want to do is to open up the lens preset. In this case, I know this is a GoPro Hero 7, so I'm going to, take a look and find the lens presets folder. And I found that the GoPro Hero 7 version 2, a preset file, that has worked fairly alright-ish for many of the GoPro cameras I've tested. But preferably, we preferably want to have separate presets for all the different cameras. But in this case, we have a Hero 7 and then matches with the Hero 7, so that's all fine. What it's going to do a bit in the background is to make sure that they somewhat match. So if the aspect ratio between the preset and the video file don't match, it's going to show an error message. But it's not going to do any other checks at the moment. So make sure that the preset and the video file, they match up. Over here, we have a few more options. We have an option for the FPV camera angle, and we have an option for the low pass filter cutoff. In this case, I know that the nicecrash did the test by having the camera oriented directly horizontally. So in this case, the camera angle is going to be 0. For the low pass filter, in some cases, you may see that the gyro track is a little bit noisy. Yeah, it's going to be fine in this case, but if you see an excessive amount of noise, you can write a value something like maybe 200 or so. So that's all for the input. Let's now go over to the sync and stabilization tab. And this is where most of the interesting stuff is happening. In the first field, we have the initial rough gyro offset in seconds. In the beginning, it is assumed that the gyro track and the video start at the exact same time. So if you input a positive value for the rough gyro sync, it's going to shift the gyro track to the right. And if you use a negative value, it's going to shift the gyro track to the left. In other words, if you start your video recording and let's say wait 30 seconds and then start the gyro recording, you want to write 30 seconds in this box. The value doesn't have to be precise, it just has to be within a few seconds. Now the next two fields, they are the autosync timestamp 1 and autosync timestamp 2. It's going to analyze different sections or 2 sections of the video using optical flow. This means that you need to pick places in the video where there's some movement. I found that having some wobble works quite well. But I've also seen that it can work if you use smooth movements, but yeah. So what we want to do now, let's actually just open up the video file. Let's see. Nice crash hero 7.mp4. We can just open up, I'm using VLC, but you can use your favorite video player. So yeah, so at the moment it doesn't actually have an integrated video player in the stabilization utility. So we want a separate video player. It's a bit annoying, but I mean, you saw how buggy the video player in the calibration utility was. So let's take a look at the video. We want to pick points in video where there's some movements, but nothing is vibrating around too crazy. We want just slight movements we can use for synchronization. In this case, we can use the initial takeoff where there's a little bit of movement, and that's at around 5 seconds. And you can see that by default, the autosync timestamp 1 and 2 are set to 5 seconds after the beginning of the video and 5 seconds before the end of the video. So the first one is probably going to be all right. Let's take a look at the second one. Let's pick this place where there's like a little bit of movement, but it's mostly hovering. So this is at around 30 seconds. So let's write 30 seconds. It also seems to work fairly well if you have a somewhat smooth flight, a somewhat smooth horizontal flight, but just try it a bit. Places which would work well for traditional optical flow-based stabilization methods are probably going to be good places to sync. Now the next one is the number of frames to analyze per slice. What it does is it analyzes a number of frames for each of the 2 timestamps. And by default, it's set to 60, and that seems to work fairly well. If you have slow and smooth movements, you may want a larger number of frames. And if you have small vibration type movements, you can probably go by having just 30 frames. The next one is the sync search size. We initially define a rough offset, but the sync search size is going to be the size of the interval it's going to look for the sync. So if you have 10 seconds as is the default, it's going to use your initial rough sync and look 10 seconds in the future and 10 seconds in the past, or rather 5 seconds in the future and 5 seconds in the past around the initial rough sync. And 10 seconds work fine. You can go all the way up to a larger value if you want. This is the smoothing method, and by default it's this slurp-based infinite impulse response filter. It's the only one implemented at the moment, but so just pick that. The next one is the smoothness, and it may be a bit confusing as to what the values here mean, but basically just take a look at the time constant, and a larger value for a time constant means that slower movements are going to be smoothed out. By default, it's set to 20%. The percent doesn't really mean anything, and we can just use this for now. You can tweak around if you want. The FOV scale, or field of view scale, is going to determine how zoomed in the result is. For now, just leave it at 1.5. You can tweak it if you want, but just leave it for now. And it is now time to do the synchronization. There's this button to display the plots during sync, and I recommend having this on, at least in the beginning, just to make sure that everything is working correctly. So let's now click on Apply and Compute Sync. And over on the left-hand side in the command prompt, we should see something happening. Right now it is analyzing the first batch of frames using optical flow. And this is going to take a few seconds, depends on the number of frames you have selected, as well as the resolution of your input video. So if you give it a few seconds, it should now have, so you can see now after analyzing the frames, it's going to estimate the rotations based on optical flow and try to compare the rotations to the gyro track. Afterwards, a plot is going to appear if you selected the plot option. What you see here on the horizontal axis is going to be the time offset. And on the vertical axis, we see the error between the gyro rotation and the video rotation. What you want to see is that there is one point in this interval going from -5 to +5 where the error is minimized. And this is what you want to see essentially. You want to see a sharp negative value or sharp value, which has a value close to 0. In some cases, you may see multiple values, and in that case, you need to make the judgment about whether the lowest value is actually the correct one. The blue curve is going to be the initial rough analysis, and the orange curve is going to be like a fine tuning on top of that. So it's going to be located at the bottom of the valley. In some cases, you see that the value over on the left-hand side at the bottom of the valley is going to be a high value. It could be something like something above 5. And that could mean a few different things. It could mean that the place you used for synchronization is not that optimal, or it could alternatively mean that there is something going on with your camera angle or your lens calibration, since all the rotations are calculated based on the lens presets. Now let's close this one, and after a few seconds it's going to do the same thing for the second track. And you can now see that the estimated offset for the second track is approximately -2.7 seconds. And what you should see is that the estimated offset for the first sync is pretty much equal to the second sync. If you have a second estimated offset, which is a few seconds slower or faster than the first one, that could mean that the two don't match up. And now let's take a look at this error plot once again. And we see something similar as before. We don't have such a sharp defined peak, actually, or sharp defined value. Actually, no, it's all right. So if we zoom in a bit, there's a trick. If you click on this pan button, you can use the right mouse button to zoom around. Yeah, you can see even though it looked quite flat when zoomed out, we can see that if we zoom into the point it actually picked for the synchronization, there's a very sharp value. And once again, we see that the error is quite low. It's below 1, which is usually a good sign. So now let's close this one, and another plot should appear. This one is going to visualize the gyro track and the video track on top of each other. The green one is going to be the gyro. And if we remember where we put the synchronization points, the first one was around 5 seconds. So let's use the right mouse button to zoom in at 5 seconds. Right. So we can see here that they seem to match up rather nicely. We can see that so the first one is going to be the pitch axis, the second one is going to be the yaw axis, and the final one is going to be the roll axis. And we can see more or less let's take a look at the last one, for instance. The green curve and the blue curve, they seem to match up mostly. Let's now also take a look at the second one, the second sync, which was located at around somewhere around the end. Oh, here we go. And there's a little bit of a high frequency noise going on, but we should see that they seem to match up rather nicely. Something which you can do if you don't want to see all of these this noise in the gyro data is to go back over to the input and write a low pass filter. So let's just use something like 100, and then do the sync once more. And we can now see that the gyro track has been smoothed out a little bit by using a low pass filter. Now, after doing the synchronization, hopefully successfully, you should see two values appear down below. And these are the delays found for the two syncs. If you find by manually inspecting the graphs that one of them is slightly off, maybe off by a few frames or something, you can go in and change these values. And after clicking on sync correction or update smoothness, it's going to display the same plots as well. You also need to click on this button if you change the value of the smoothness. Now let's go over to the export tab. We have a bunch of different options once again, and you really want to, there's something that you want to change. In the first one, we see the output crop. By default, it's going to be set to the same resolution as the input file, but you really want to change this if you don't want to do a whole bunch of cropping afterwards. For the next one, we have the output upscale. Now this may seem a little bit backwards, but the output crop is not actually the resolution of the final file. You can view it as if you take the input file, you do all the stabilization stuff, and then you crop down and you upscale the final result. But in reality, it's going to do the upscale in the beginning just to keep all the resolution. For the next one, we are going to define the start and stop time of the video. And by default, it's going to be pretty much the whole video. Let's try to go from 5 to 10 seconds, just to have a nice short slice of the clip. We also have a few options over here. They should be fairly self-explanatory. And in this case, let's just enable hardware encoding. Hardware encoding was added by Alex AGV over on GitHub, by the way. For the next two options, we can leave them alone for now and click on export, hopefully stabilized video. And let's just define a place to save it. I'm going to override this one. And you should hopefully see that a preview window is going to appear. You can see that there are a bunch of black borders around the edges, and these can be cropped away by using the export crop setting. Alternatively, you can also do just a little bit of cropping here in Gyroflow, and then load the file over to your favorite video editing application where you can maybe zoom around or do whatever you want. Something which can be useful is that if you have a wide angle fisheye lens and you started off using a 4:3 aspect ratio video, you can crop down to a 16:9 video, since the distortion makes the final result wider. So let's say we want to crop down to 1920 by 1080, and you can upscale the video if you want, but let's just leave it to 1 for now. And you can change these values however you like, but let's just export this one. And you should see that the video has been cropped a little bit. In some cases, you may see that the final result doesn't seem to play in a bunch of video players. This can be caused by something going on with the chroma subsampling. So you can try to use YUV 420p in this box. You can also, if you want to, try to use a different FFmpeg encoder. If you run the command ffmpeg-encoders, you can see all the ones available if you have FFmpeg installed on your system. I did a super quick test using ProRes and it seemed to work all right, but of course none of this, or most of these, aren't tested yet. So yeah, you can use them at your own risk. Let's briefly cover what it is like if you're using a GoPro file. It should be noted that this tool is still a lot worse for GoPro files or stabilization in general compared to Real Steady Go. So if you have something like a GoPro Hero 6 or a GoPro Hero 8, you should really just get Real Steady Go if you want to use it for anything serious. So let's suppose this is a GoPro Hero 8. We can now go down in the camera type selection and select the GoPro Hero 8. And the reason for this is that the different cameras seem to have different gyroscope orientations. So you need to select the right one here to match whatever GoPro camera you're using. You also want to select the right lens preset, of course. Now let's take a look at the final result of this quick test. And let's now briefly go over some of the parts of the process which may go wrong and how to identify potential problems. If you see in the final result that the stabilized video is somehow overcorrected or undercorrected, or if you see that there's a bunch of wobbling around the edges of the image, this means that something has gone wrong with your lens calibration. If you see a bunch of wobbling at high frequency movements, this is probably going to be rolling shutter distortion, which is something that is currently being worked on but hasn't been implemented yet. If you see high frequency jitter, which is still present in the stabilized results, even though the majority of the major movements are stabilized, this means two things. One of them could be that there's excessive noise in your system, something like a bad flight control, gyro, or maybe something to do with your soft mounting solution. You can try to mess around with the low pass filter settings to see if you can solve this problem. Another potential cause for high frequency jitter in the stabilized results is a synchronization that is ever so slightly off. I found that even a synchronization that is off by one frame could cause noticeable amount of jitter and vibrations. So take a look at all the plots and make sure the movements line up. A trick I found is to use prop wash oscillations for synchronization. They are fairly high frequency vibrations, which are good indicators to compare the gyro and the video. If you have any problems, you can try asking over in the Facebook group or in the Discord server, or maybe even open an issue over on GitHub. I know this video has been a bit long, and I'm not sure how many people are going to watch till the end. Hopefully a few. So I'm going to end up by saying thanks to everyone who has shared test clips for use during development. This project would not have been possible without you. Also, thanks to everyone who has helped out by adding bits of code over on GitHub and those who have tested out the earlier versions of the software. It's honestly somewhat exciting to work on something which people are going to use maybe, and which may actually be useful for once. If you want to help out, the best thing you can do is probably to try out the software and share your results. You can share them over in the FPV Stabilization Tools Facebook group or in the RSGO Blackbox Discord server. This is all still very much in alpha, and I appreciate everyone who share their results and share what works and what doesn't work. The number of default lens presets is also quite low, so if you try out a new camera, I do encourage you to send the lens presets to be added as well. And finally, I know everything is still a bit rough, but if you appreciate the effort that has gone into research and testing and all that, and perhaps want to support future development and potentially even more hardware testing, there's also a little donation button on the website or maybe in the description or somewhere. You can probably find it. But anyways, that's all. I'm looking forward to seeing the results.